given information with more regression models, what I want you to do at the top of the notes is see what you recall from day one. What I'll tell you is that first and foremost, not all sets of data will have a linear relationship, and a line of best fit is not always the best model for any given data set. So we're going to look at and explore other functions today that might model a set of data better than a line. I want to see if you can remember what the general forms look like for these models below. So we're going to look at maybe some quadratic, exponential, logarithmic, and examples of power today. And then once you're done with that kind of little chart there, if you don't remember what the equation looks like, maybe just make a quick sketch of what you think that might look like. Hit pause real quick, and then I'll show you what my results look like. So in this setup, we have, those are the general forms for each of those equations that we actually wrote in yesterday's notes. So hopefully you remembered most of them. Here's what the sketch of the graph might look like based on those equations. Again, it doesn't have to be a positive slope for a linear. We saw plenty of examples where there's negative slopes. So just kind of a quick, somewhat general sketch to remind you what each of those functions look like. Okay, let's go ahead and jump right into it. Here's a set of data. It says when debris is dropped off from a cliff, its height h is measured in feet at various times t measured in seconds. And it's shown in the table below. So here's the times, here's the heights. Use the given set of data to construct a scatter plot where time is independent and state the quadratic regression equation, which models this data. We're going to round to the nearest thousand. So the nice thing about regression and what makes it, I think, pretty easy as the topic is that you're told what type of regression to do. You don't have to look at the data and make a determination on your own. It says straight up, just do a quadratic regression here. So I'm going to go to Stat Edit, go ahead and clear out my lists. And let's type in, we've got for list 1, 0 through 5. And then in list 2, we've got some heights. Okay. So we're going to state the quadratic regression today for this specific example. So I'll show you where to find that. But I believe I even showed you when you go to Stat and then over to Calc, there's all our regression models are going to be waiting in here for us. So we will not use all of them, but we can do a quadratic regression. So if I choose option 5, we've got L1 and L2 set for our lists. I'm going to store the regression equation just like I did yesterday, so I can see what the model looks like against the set of data points in our scatter plot. So I'm going to go to vars, over to yvars, and hit enter for function, enter for y1. We'll hit calculate. Don't worry too much about the r squared value here. You would learn more about what that implies about this given data set in AP Stats if you're going to take that next year or as a senior. But remember, if you hit that zoom 9 function, yeah, this given set of data, it really makes sense to me that we would model this with a curve a little bit nicer than we can model it with, let's say, a linear function. So we can see how nicely that quadratic model fits the data. Let's go back to the quadratic model so I can see what the equation was rounded to the thousands place. We've got negative 19.143 for the value of A, 17.6 exactly for B, and then we'll round that 861.143 for the value of C. So we just have to make sure we plug in those values into the general form given at the top. So we've got y equals negative 19.143 x squared plus 17.6 if you want to make sure that that's rounded to 3 decimal places so it doesn't look left out. We'll put a 0, 0 after that. That's the coefficient of x plus 861.143. Okay. So then it says, using this equation, find the approximate height rounded to the nearest foot of the debris at time equals 7 seconds. This would be an example of extrapolation, right? 7 seconds is after the last time that we have in our data set given. So, but more importantly, we have to know where are we plugging in 7? Is it an x value or a y value? And time, that independent variable, is going to be an x value. This was all my list 1. This is my list 2, right? Okay, so go ahead and plug in 7 for x and just evaluate. Negative 19.143 times 7 squared plus 17.6 times 7 plus 861.143. If you type that into the home screen on the calculator to the nearest foot, you should get that the height is about 46 feet. Pretty close to the ground at that time. And then predict at what time to the nearest tenth of a second the debris will hit the ground. So like I said in the last part, we know we're pretty close to the ground at 7 seconds, but to the nearest tenth of a second, we can determine when this hits the ground. So if it's hitting the ground, that would imply that the height is 0 feet. And since height is a y value, you're going to go ahead and you're going to plug that in for y, and you're going to solve. And there are really two different methods, and it doesn't say how to do this here, but we'll kind of talk about both. Let's talk about the method that I'm assuming many of you would choose, which is graphically. And why not? We already have the model typed in to y1. Y1 would be your quadratic regression model. And although there's other ways around it, I'm going to do y2 equals 0. And then what we're going to look for is to calculate the intersection there. And when I calculate the intersection, that's going to tell me when the height is 0. So go back to your y equals screen. You'll notice that we have that very large quadratic regression model typed in. Y2 is going to be 0. Go back to Zoom 9 there. Let's see if I can even see that line y equals 0. Not sure. Yeah, I'm guessing based on the window that it's not showing me the line y equals 0. So if I go to my window, I'm going to adjust the y min. The y min right now is 377. So I definitely want to make that go. Let's go to like negative. Let's go crazy. Let's go negative 500. You can see how that really changes the appearance of what that data originally looked like in our viewing window. Okay, I don't know if you can see on my screen, but there was a red line that came across for the line y equals 0. This definitely doesn't happen within our scale for x. We know it's going to happen after 7 seconds. Let's go back into the window, adjust maybe your x max to 10 seconds. Okay, and now we should be able to find that intersection point. So now that I have this all set up, you're going to hit second trace. We're going to calculate choice 5, the intersection. Scroll near that point of intersection, hit enter 3 times, and we get 7.2 to the nearest tenth. So this would take 7.2 seconds. Let's talk about a way that I'm also hoping you're fairly confident with, although I know the default probably might be to do it graphically. If I were to do this algebraically, I would have to take the equation, negative 19.143x squared plus 17.6x plus 861.143, set that equal to 0. And I'm really hoping you're not going to try and sit here and do some sort of factoring or even thinking about completing the square. I mean, what a mess that would look like if you had to complete the square. So I'm really hoping you would default in this case algebraically to using quadratic formula. Okay, definitely have to be confident with that if we're going to be successful in a pre-calculus class next year. So you would plug in the correct coefficient values into the quadratic formula. Maybe you're even singing it in your head right now. And you should get, you may not get exactly 7.2, by the way, because these are rounded coefficients as opposed to what I had typed into y1. But hopefully you get something pretty close to 7.2 if you try the algebra over here. Okay, so in the interest of time, if you want to try that, go for it. But I'll just leave it there and say definitely go with quadratic formula on that. All right, on the next page, we've got an example of a radioactive element present that deteriorates according to its half-life. We have done half-life examples this year, so I'm hoping that's taking you back to our unit on exponential functions. So here's the table of the number of days that have elapsed and then the amount of that radioactive element that's left after those days have gone by. So we're going to get a scatter plot going and determine the exponential regression equation that models this relationship rounded to the nearest thousandth again. So go ahead and edit your list 1 and your list 2 here. Okay, clear that out. So we've got 0, 2, 4, 6, 8, 10. And then we've got 360, 230, 180, 120, 90, 60. Okay. So once you become pretty confident with regression, you start kind of remembering what numbers they are in StatCalc. So if I go to StatCalc, you won't even see exponential regression in this initial list because it happens to be choice 0. So the easiest way to get to exponential regression is just by hitting 0 when you're in StatCalc. But if you scroll down, you can pretty easily access that. I'm going to store the regression equation in Y1. So remember, I've been doing bars, Y bars, enter, enter, and then go to hit calculate. Okay, here's the exponential model. I'll write it down while I have it here, and then we'll look at the scatter plot too. So we've got to the nearest thousandth, the value of A is 348.300 is what that rounds to the thousandths place. And the value of B is 0.840. Okay, make sure you're following the appropriate model. And the nice thing about any regression models, it tells you exactly how you're supposed to write out with the coefficients of A and B plugged in. So there's my equation. Let's go ahead and check out the scatter plot real quick, see just how exponential it looks. It should look like exponential decay, right? It's going to be going down from left to right because of the half-life example we're looking at here. So zoom 9 gives us that model. And then look how nicely this curve fits the model here. We shouldn't expect it to contain every single data point, but look at how closely grouped those data points are to the exponential model of best fit here. Part B, using this equation, determine the number of days it will take for only 20 grams to remain. So 20 grams, that's going to be according to the table a Y value. We're looking for number of days, which is an X value. So we got to plug in 20 for Y. And then we got to solve for X. Okay. You can do this algebraically. You can do it graphically. I think graphically is going to be pretty easy for you guys. So I'm going to let you try that one on your own. I'll do it the tough way, which is the algebraic way. Algebraically, when you're solving an exponential equation, I hope there's one key word that's really jumping out in your mind right now. And it happens to be logs, right? So first of all, divide that amount over that A value to the other side. And this is going to be a nice number by any means. If you want to express it as a rational number without that decimal there, the calculator would tell you it's 200 or 3,483, right? And then from there, if you take the log base 0.84 of both sides, this side would just become X. But essentially, the way that you're going to solve for X is by doing the log base 0.84 of my fraction 200 over 3,483. So what I love about regression is it brings back all of those functions that we learned so long ago, but maybe have forgotten about a little bit as time has gone by. Okay, these are all really key critical functions for what you'll be studying the next 2 years in high school math. So we can do log base on this one. If you hit math and scroll up, you got log base there. We want log base 0.84 of 200 divided by 3483 to get that this takes approximately how many days? We'll go to the nearest day here and we'll say that it takes about 16 days, right? So sometime during the 16th day is when this will happen. Okay. Hopefully that made sense. And you know what? Why not try it? Go to Y1, Y2. Y1, you should already have that exponential model typed in. Y2, you would type in 16, calculate the